This next section is going to cover section 4.4. This next section is going to cover section 5.4 and 5.5 of the homework. The concepts we're covering are going to be the properties of rational functions and their graphs. Please note that this is section 5.5 and 5.6 of the text if you were looking into the text for a reference. So a rational function is defined by a quotient, i.e. fraction, of polynomials that has the form f of x equals p of x over q of x, where p of x and q of x are both polynomials, but q of x doesn't equal 0. Okay, and it's really important that the denominator never equals 0 because we can't divide by 0, it's undefined. The domain of the rational function is all real numbers except those that would make our denominator equal to 0. Okay, so this is because we cannot substitute in any x values that would make us have to divide by 0. So the way we find domains is this. What I want to do is I want to factor the denominator. Factor the denominator. I need to set the denominator equal to 0 and solve for the points not included in the domain. I then want to write that domain in set or interval notation. So let's take a look. I've got f of x equals 3 over 7x minus 14. So if I set my denominator equal to 0, I add 14 to both sides. I get that 7x equals 14, so x equals 2. 2 cannot be substituted in my domain. It cannot be an x value in my domain. If I was to substitute in 2 for x, I would get 0. 7 times 2 is 14, minus 14 is 0. So my domain in set notation is x such that x doesn't equal 2, or it's all real numbers from negative infinity to 2 and from 2 to positive infinity. So here's set notation and here's interval. Interval notation gets a little bit more complicated as our domains get more complicated. So let's take a look at this second example. I have f of x equals 3 plus x over x squared minus 4x plus 3. I need to go ahead and factor this denominator. I think, okay, what are the factors of 3 that add up to negative 4? And that's going to be negative 3 and negative 1. So I set each of these equal to 0. And I find that x equals 3 and x equals 1. Those are the two values I'm leaving out of my domain. So this is a little bit simpler in set notation. It's all x values such that, that's what this vertical bar means, such that x doesn't equal 1 or 3. In interval notation, it's important to think of a number line. Remember that the two values I'm skipping over are 1 and 3 because those can't be included in my domain. So how can I write this graph in orange as an interval? Well, it goes from negative infinity to 1, and then it skips over 1, and it goes from 1 to 3, and then it skips over 3, and it goes from 3 to positive infinity. So that's how I'd write this in interval notation. It's important to note that there are some special case domains. For example, if I have 8x plus 3 over 3, my domain is always positive. My domain is actually always 3. So 3 can never equal 0, so my domain, in this case, is all real numbers. So it goes from negative infinity to positive infinity. The same is true for f of x equals 2 over x squared plus 4. This domain can never be negative because x squared is always positive. A positive number plus 4 is always going to be positive. So because my domain is always positive, it can never equal 0. Even if x was 0, we'd have 0 squared plus 4, which is 4. So my domain can never equal 0, so my domain also goes from negative infinity to positive infinity. We can also find the x and y intercepts of any graph. Remember that if we let x equal 0, then we find our y intercepts. And if we let y equals 0, or f of x, right, we find our x-intercepts. So let's go ahead and let x equal 0. If I have f of x, f of 0, equals 3 over 7 times 0 minus 14, I get 3 over negative 14. So my y-intercept is when x is 0 and y is 3 over negative 14. To find my y-intercepts, to find my x-intercepts, I let y equal 0. So if I have 0 equals 3 over 7x minus 14, I can multiply both sides by 7x minus 14. Well, 0 times 7x minus 14 equals 0. So I get that 0 equals 3. This is not true. What does this mean? This means there are no x-intercepts. Okay, well, what if I don't believe that? Why don't we go ahead and graph this? So let's go to Desmos. So I'm going to go ahead and graph f of x equals 3 over 7x minus 14. And we're going to learn more about how to graph these later. But as you can see, I don't have an x-intercept. My graph gets really, really close to 0, but it never quite touches 0. So what we have there is an asymptote, and that's going to be the focus of this chapter, but there is no x-intercept. We did, however, find that our y-intercept was really close to negative 3/14. All right, let's take a look at our second example. I have f of x equals 4 plus x over x squared minus 4x plus 3. And I'm going to go ahead and solve for my y-intercept by letting x equal 0. So f of 0 equals 4 plus 0 over 0 squared minus 4 times 0 plus 3. So I get 4/3. My y-intercept is when x is 0, y is 4/3. Now I can go ahead and solve for my x-intercept. My x-intercept is when y equals 0. So if I have 0 equals 4 plus x over x squared minus 4x plus 3, and I multiply both sides by the denominator, because that's what we have to do, even though it's weird. That gives me 0 equals 4 plus x. So if I divide 4 from both sides, I get that negative 4 equals x. So my x-intercept is when x is negative 4 and y is 0. I have found my x and y intercepts. This is going to be really important to helping us graph rational functions. We're going to need to know what values are excluded from their domain, their y-intercepts, x-intercepts, and also their asymptotes.